Pluto made them come up and down. Pluto's circle crosses that of another planet. Pluto, the confounding little planet at the outside extents of our close-by planetary bunch, is stirring up intensity in the world of space science. Progressing reports show a possible encounter with Neptune, raising concerns among specialists and space fans. Unmistakable figures like Neil deGrasse Tyson and Michio Kaku have sounded alarms about the repercussions of this galactic occasion. Yet how did Pluto end up on an intensive lesson with its bordering planet? Furthermore, what could this heavenly struggle mean for life on Earth? Join us as we unravel how something immense just collided with Neptune and how scientists have been left anxious by this tremendous inconsistency. Pluto, once hailed as an obvious planet, went through a change in its status, being renamed as a dwarf planet because of its unusual orbit. Nonetheless, this minimization, Pluto still charms and interests the cosmic community. Later assumptions from regarded analysts like Neil deGrasse Tyson and Michio Kaku have raised concerns about Pluto's trajectory possibly meeting with Neptune, demonstrating an approaching series of encounters between the two glorious bodies, which could have significant repercussions for Earth. Pluto's excursion around the Sun stands out due to its extraordinary qualities. Within our planetary gathering, its circle is strangely elongated, crossing a dazzling distance since its discovery in 1930. Pluto has yet to complete a full orbit around the Sun, adding to its persona. The exceptionally extended condition of its circle is a departure from the more round paths followed by the major planets. Other than Pluto's circle drifts off by 17 degrees from the ecliptic plane, giving its path a more extreme tilt compared to different planets. The combination of Pluto's inclination and its bended circle presents layers of intricacy to its orbital pattern. One remarkable aspect is its intermittent intermingling with Neptune's circle. For around 20 years during each cycle, Pluto ventures closer to the Sun than Neptune, contradicting assumptions based on their different positions in the nearby planetary gathering. Plunging further into Pluto's circle, it's captivating to note that it's not a perfect circle, but rather an elongated path resembling more of an oval shape. This unusual orbit results in significant variations in Pluto's distance from the Sun throughout its journey. At its nearest approach, Pluto comes within around 30 astronomical units, AU, of the Sun, while at its farthest point, it reaches in excess of 49 Australian dollars away, twice the distance of Neptune from the Sun. Additionally, Pluto's orbit is tilted at a critical angle compared to the orbits of the major planets in our planetary system. This inclination not only adds to the complexity of its orbit but also plays a significant role in its interactions with other glorious bodies, particularly Neptune. When Pluto encounters Neptune, their gravitational influence alters their trajectories over time. The complicated dance between Pluto and Neptune highlights the unique nature of our nearby planetary gathering. While Pluto was once seen as a solitary stray in the outer reaches, its nearby encounters with Neptune emphasize the interconnectedness of celestial bodies, each applying gravitational forces that shape the orbits of others. In recent years, advancements in observational technology have allowed astronomers to track Pluto's movements with great precision. This has led to a deeper understanding of its orbit and its possible implications for the stability of the outer solar system. While the probability of an immediate collision between Pluto and Neptune remains low, the possibility can't be entirely dismissed, provoking observatories and studies by the galactic community. Regardless of its unobtrusive size and distant location, Pluto continues to command attention and interest among researchers and enthusiasts alike. The question arises, why hasn't there been a collision between Pluto and Neptune? The answer lies in the gravitational pull from other planets. Astronomers began studying Pluto's path soon after its discovery, and its orbit baffled them. Unlike most planets that stick close to the same plane as they orbit the Sun, called the ecliptic plane, Pluto stands out with its steep angle and oval-shaped orbit. The mystery deepened when they realized Pluto's path crosses Neptune's. Despite these complexities, Pluto's orbit remains stable, demonstrating the intricate mechanics of space. Grasping how three celestial bodies move and interact gravitationally, like Pluto, Neptune, and the Sun, is a critical challenge. It's akin to attempting to predict where they'll go based on where they start and how they pull on one another. For Pluto, this challenge reveals how its path, Neptune's path, and the sun's coordinate all work together like a complex interplay. Terms like precession, libration, and the VSOP variations help researchers in solving this astronomical riddle. Understanding these dynamics is crucial for keeping planets in their orbits. When Pluto crosses Neptune's path, it's still about 90 degrees away, preventing them from colliding. Libration ensures that when Pluto approaches Neptune or other large planets, it remains well above their path, reducing the likelihood of an impact. The VSOP variations, named after researchers von Zeipel, Poincaré, and others, explain why Pluto's orbit appears unconventional yet remains predictable over time. Despite the chaos in space, some patterns and rules keep things in order. These principles stabilize Pluto's orbit, preventing collisions with Neptune or changes in its path. The chance of orbital mayhem demonstrates how a celestial body's orbit is highly sensitive to where it begins. Even small changes in its position or speed can disrupt its orbit over time. Researchers use computational simulations to figure out how Pluto moves in space. These simulations utilize complex mathematics to mimic how Pluto interacts with other celestial objects like Neptune. By tweaking these simulations just a bit, astronomers can see how tiny changes can alter Pluto's orbit. In the late 1900s, these simulations found something intriguing about Pluto's orbit. Despite the factors that should make it stable, Pluto's orbit can still be capricious. Just a slight difference in where Pluto starts or how fast it's moving can create significant changes over many years. However, even with this chaos, Pluto's orbit remains stable for extended periods, like billions of years. This suggests that although Pluto appears turbulent, its journey around the Sun follows a sort of pattern. Predicting what will happen with planets like Pluto, which have eccentric orbits, is challenging. These systems are so unpredictable that it becomes difficult to foresee what will happen in the long term. Simulations help us learn about potential outcomes, but they also show us that we cannot predict everything. Understanding Pluto's orbit is essential, especially when considering whether it could collide with Neptune in the future. This knowledge helps us gain insight into how our solar system operates. Pluto's orbit teaches us that even orbits that seem unstable can stabilize due to gravity and the dynamics of space. Continuing to observe and study these phenomena is fundamental for expanding our understanding of the universe and our place within it. When we explore space, we discover that things can be strange, and Pluto's orbit is a prime example of that oddity. Pluto's orbit is unlike those of other planets. It's more oval-shaped, which means it's not a perfect circle. Sometimes it even draws closer to the Sun than Neptune does. This can create interesting dynamics because Neptune is also cruising along its path. There's a slight chance that Pluto and Neptune could collide in the end. Despite its peculiar orbit, Pluto manages to avoid Neptune most of the time, thanks to something many refer to as gravitational forces. Gravity is like an invisible force that pulls things toward each other. So, although Pluto and Neptune might seem to be on a collision course, their orbits are carefully arranged, guided by the pull of gravity. Pluto's orbit teaches us that space is full of surprises. What seems chaotic at first glance can be a delicate balance of forces. By studying Pluto's orbit, researchers gain insights into the complex mechanics of our solar system. This ongoing observation and investigation are essential for expanding our knowledge of the universe and our place within it. Imagine if Pluto and Neptune did collide. It would be a galactic event, sending shockwaves through our understanding of the nearby planetary system. While we've made progress in understanding space, what's happening suggests that we still have a long way to go. Focusing on what large planets mean for Pluto's path gives us significant clues about how our entire nearby planetary system operates. It shows us that where each planet is and how it moves can change the paths of other objects in space. Despite the complexities of space, the fact that Pluto could potentially crash into Neptune concerns researchers. This raises the question of why such a collision could occur, even though it seems improbable. Neil deGrasse Tyson, a prominent astrophysicist, has some intriguing thoughts about Pluto. He believes that renaming Pluto as a dwarf planet, rather than a major one like Earth, is a step forward. He feels that we are constantly learning new things about how objects move in space. Tyson sees Pluto's odd trajectory as a sign that there's still much we don't understand. He believes that the mysteries of space are captivating and that significant events, like Pluto's renaming, engage people in space science. Tyson wants to help people grasp the cool and sometimes strange aspects of how space functions. He emphasizes that discussing space mechanics can amaze us. Tyson collaborates with various researchers to warn people about the potential risks of Pluto's unusual orbit. After focusing on Pluto extensively, the fact that it could collide with Neptune one day concerns him. He suggests that such a collision could create enormous problems for our entire solar system. A mishap between Pluto and Neptune would be a captivating and serious event. It would release a tremendous amount of energy and could break apart Pluto, with fragments zooming around space and potentially hitting other planets and moons. Neptune could also feel the impact, altering its movement. Famous theoretical physicist Michio Kaku, known for his contributions to string theory and science communication, offers an interesting perspective on space exploration. He firmly believes that understanding the fate of space travel and the relationship between celestial mechanics and theoretical physics can be gleaned from studying peculiarities like Pluto's orbit. Kaku considers Pluto's orbit to be a window into the future of space exploration. By comprehending the complicated gravitational interactions and orbital elements of celestial bodies like Pluto, we can improve future space missions, aiding in safer navigation through the solar system, predicting potential dangers, and planning missions to distant corners of our vast universe. Kaku emphasizes that patterns learned from Pluto's orbit can be applied to exploring other glorious bodies, providing a roadmap for interpreting distant worlds. He often highlights the profound connection between celestial mechanics and theoretical physics, underscoring that the movements and interactions of planets, such as the gravitational dance between Pluto and Neptune, are rooted in fundamental principles of physics. Kaku's work in theoretical physics, especially string theory, aims to unravel these principles at their core. He suggests that focusing on the complexities of celestial mechanics, like Pluto's orbit, can yield insights into the fundamental laws of the universe. Like Tyson, Kaku has also contemplated the potential impact of celestial bodies, relating it to his theories about the universe. A collision between Pluto and Neptune, while significant in astronomy, could offer a unique observational opportunity, potentially contributing to our understanding of string theory. String theory, which replaces point-like particles with one-dimensional strings, seeks to describe the fundamental forces and matter in the universe. Such a collision could create extreme conditions of energy and gravity, shedding light on the behavior of fundamental particles and forces under extreme circumstances. Furthermore, the gravitational waves produced by such an impact could provide valuable data for testing predictions of string theory concerning spacetime. While the immediate effect on Earth would be negligible due to our distance from the outer solar system, the scientific implications could be profound. Understanding events like this could broaden our interest in the fundamental nature of the universe as characterized by string theory and other areas of theoretical physics. Its fascinating attributes, influenced by the gravitational forces of neighboring planets, particularly Neptune, highlight the intricate and dynamic nature of space. However, the universe holds many secrets, and the three-body problem is just one of them. Researchers anticipate other potential disasters, highlighting the ongoing quest for understanding and exploration in the vast universe. Although it's highly unlikely, there's still a slight chance of planets colliding in space. This can occur because planetary paths are influenced by various factors, such as gravitational pulls from other planets, a phenomenon researchers refer to as the three-body problem. In systems like the TRAPPIST-1 system, where there are 7 Earth-sized planets, the gravitational forces create a sort of dance in how the planets move, leading to orbital resonances over time. These resonances can make a planet's orbit less stable and could potentially result in collisions. Although systems like TRAPPIST-1 are interacting with their planets, impacts aren't occurring right now. Researchers keep an eye on these systems to understand how planets influence each other's paths, especially when they draw close. This helps us learn about planetary movement in space. Sometimes, there are rogue planets that do not orbit a star and drift through space irregularly. These planets used to be part of a star system but were ejected due to gravitational interactions or when another star came too close. Over time, these wandering planets can traverse vast distances and may collide with other star systems. However, since space is mostly empty, the likelihood of them hitting another planet is very low. Rogue planets are intriguing compared to the number of stars and planets with stable orbits, making collisions even less likely. When galaxies collide, it can disrupt the orbits of the star systems within them. Although planets probably won't collide directly during these massive events, gravitational interactions can alter how stars and planets move. Sometimes, planets get flung out into space, becoming rogue worlds. Other times, they may collide with one another or their host stars. These disturbances can indeed create new celestial bodies or form new stars. The late heavy bombardment theory suggests that around 4 billion years ago, there was a period of increased impacts, including comets and asteroids. This bombardment is believed to have occurred because the outer planets, like Jupiter and Saturn, were moving around a lot, disrupting the orbits of many smaller objects in space. As a result, these smaller objects were thrown onto eccentric paths, many of which ended up in the inner part of our solar system. This led to a significant increase in impacts on planets like Earth. While these impacts didn't involve planets colliding directly, they demonstrated the reality that gravity can make large changes to how things move in space. This barrage shaped the surfaces and histories of planets in our solar system and might have even brought water and organic material to Earth, contributing to the formation of our planet.